Know where you're born and all this.
Sure.
Good. All right, here we go. Welcome everyone to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce to you Minhal Gardezi. She's with the Department of Physics. She's going to talk with us about, can X-rays trace the origins of printing? And I'll get to ask her the 5 questions. Minhal, where were you born?
I was born in Edinburgh, Scotland. For some reason.
Wow. Were you born in the castle?
No, but I was born in a building called the Royal Infirmary. So it sounds like a castle in my head.
That sounds pretty royal to me. And then where did you go for what we would consider to be the equivalent of high school?
I went to the University School of Milwaukee.
Whoa.
So I'm from Wisconsin.
And then where'd you go for your undergrad and what did you study?
I went to Wellesley College out in Boston and I studied physics and computer science.
And then you did a fellowship after that before coming here?
Yes, I did a 1-year fellowship at Harvard.
And now you're here getting your PhD in physics.
In physics.
I'm looking forward to your talk. Few things get me more excited than the technology and history of printing, because I worked, well, I did. I worked in a print shop when I was a kid. So I know. So this is going to be great. Would you please join me in welcoming Minhal Gardezi to Wednesday Night at the Lab?
Okay, hello everyone in person and online. And thank you for coming to my talk, and thank you to Thomas for inviting me to speak at Wednesday Night at the Lab. My name is Minhal Gardezi, like he just said, and I'm a second-year PhD student here in the Department of Physics at Madison in Uwe Bergman's group. And it's an X-ray research group. And today I'll be presenting my specific research that attempts to answer the question, can X-rays trace the origins of printing? So just from the title of my talk alone and all of the many different logos on this title screen, you can probably guess that my research is very interdisciplinary. I do work with X-rays, which are squarely in the field of physics, but I use them for cultural heritage studies. So what I mean by that is I am part of teams that collaborate with museums and private collectors to receive cultural heritage artifacts. These are things like pieces of artwork or documents or even dinosaur fossils, which are normally extensively studied by scholars in their respective fields. However, while historical and cultural studies are very, very important to understanding these objects and to understanding our shared cultural and natural history, there's only so much information of that type that is available. Up until a certain point, you just hit a wall because you weren't alive back then. And there are some things you just can't know, except maybe you can know them. That's where physicists come into the picture. In fact, each of these artifacts shown on the screen right now are all objects that my PI, Dr. Bergman, has studied using X-rays in the last 15 years. The first is the Archimedes palimpsest. So a palimpsest is a document whose original print was covered up or effaced in some way, and then it was overwritten with something else. This tended to happen usually with parchment manuscripts because oftentimes it was easier and cheaper to just palimpsest some old parchment than it was to actually make new parchment. And that's exactly what happened here. There's this big parchment manuscript booklet. And on the right-hand side of this image of the man sitting in the chair, that's what we see with our eyes. What's physically on the page when we look at it, it's the thing that was drawn on top of the original text. But what we see on the left is actually an X-ray image of the underlying text. Not something that we could ever see with our eyes, but we could see using X-rays. And what was actually written underneath is an original copy of Archimedes' work, specifically pieces of his work that we believe were lost forever. we were able to recover them through this palimpsest. So this experiment was hugely important in that it showcased the potential for X-rays to be used for cultural heritage studies. This next one is another palimpsest, another parchment that was palimpsested. And this one involved the work of Galen. So you may have heard of Galen. He's a 2nd century Greek physician. And his medicinal practices specifically revolved around the humors, things like, bile and the other bile. I'm not sure what the humors are, but those medicinal practices were not entirely accurate to how the human body works. But Galen's work was hugely influential in Europe, and it influenced the next several centuries of medicine. So this document here, again, by similar X-ray techniques, was discovered to be a palimpsest, and the original writing was a Syriac translation of Galen's original notes. So again, very, very important example of the use of X-rays for cultural heritage studies. And finally, the fun one, my PI got to examine a fully intact, the fossil of a fully intact Archaeopteryx skeleton. And the Archaeopteryx is the dinosaur predecessor to birds. It's believed to be the first bird or the first animal with wings that could fly. And through X-ray studies of this fossil, my PI was able to uncover more information about what this animal was like when it was alive, and specifically what it looked like, including what the actual feathers on its wings, the color pattern within them. Wow. Really, really amazing, incredible work from a variety of different fields. So all of these are examples of how we can use X-rays to see beyond the limits of just our eyes. We see things that we could never see with our eyes. And that's because we can think of each of these artifacts like little chemical time capsules. They contain a lot of information about the environments that they were in when they were created, and the time after they were created as well. And these little time capsules can be opened up using X-rays. And that brings us back to my original research question, which is, can X-rays be used in a similar manner to trace the origins of printing? So to answer this question, we first have to dive into what we're even trying to study, which is early print. Now, print refers to the process of creating documents through mechanical means. So this is as opposed to handwriting a document or hand copying a document. Print introduces some sort of machine element to the whole process. And when we say early print, we're referring specifically to the very first instances of these machines, which would be the original printing presses. So printing presses, like the one depicted in this photo, use what is called movable type to mass produce documents. So the idea behind this is you cast the letters in the alphabet you're printing in, or sometimes you cast entire words in metal, and then those little metal pieces are called types. They're like little stamps. And then you arrange those types in the order to form all the words on your page.
Older, if you put them
Here
in,
it goes off.
this is when I was in junior high.
Okay. to form the page that you want to form.
So
And then you roll ink over all of those characters, and then you press down a piece of paper on top of it. And when you lift the piece of paper up, all of those words have been effectively stamped onto the paper, and you've printed an entire paper. So while arranging the letter types may sound tedious, the idea of just being able to print hundreds and hundreds of copies of these pages rather than writing them all out, you save an immense amount of time. And so once you've printed one page, you can rearrange all the types to form your next page and print more and more copies of those, and so on, until you've effectively mass produced entire books. So before starting my research into early print, I already had a pretty good understanding of how printing presses worked. We'd kind of learned about them a little bit in school. And what I really needed to learn more about was the history of these presses. So I'm going to spend some time talking about that. So when I was learning about the history of presses, I turned to the place where all great research endeavors begin, which is, of course, Wikipedia. And this is the page, the printing press page on Wikipedia. And immediately one thing jumped out to me, which is this name, Johannes Gutenberg. This is a name that is familiar to me. It's because when I was learning about printing presses in school, we learned specifically about the Gutenberg printing press and how Gutenberg was the father of printing. And he printed his famous Gutenberg Bibles. But the other thing that jumped out to me is this sentence right here at the end of the first paragraph, which reads, typically used for text, the invention and global spread of the printing press was one of the most influential events in the second millennium. So that's a pretty bold statement to make. And it's one that surprised me, not because I didn't believe it was true, but because I never really took the time to think about it and think about why it would be true, and just how influential the printing press was. In fact, if you Google most important inventions, the printing press will always make it near the top of the list. And also, Gutenberg's name won't be far behind. Pretty much universally, the printing press is heralded as an extremely important invention invented by Johannes Gutenberg. So this raises the questions, why was the printing press so important, and what exactly was Johannes Gutenberg's role in all of it? So to sort of answer those questions, I want to lay out a very rough history of movable type print. So here's a basic timeline. And for reference, this block right here is what we call the European Renaissance. And it's right near the beginning of this Renaissance, around the mid-15th century, that Johannes Gutenberg printed his first 42-line Bible in Mainz, Germany. So as soon as these Bibles entered the world, there was almost this immediate explosion of the use of his printing press throughout not only Germany, but the rest of Europe. And just 50 years later, there's an estimated 20 million volumes printed using these presses.
That's
and
amazing.
By the end of the Renaissance, there's about 200 million volumes printed. Wow. So this is an immediate, widespread use of these presses to print all sorts of documents. Gutenberg's first motivation to come up with this press and to print the Bibles was because he wanted greater accessibility of his religion. Previously, because all these books were hand copied, to get your hands on a Bible, you needed to have some sort of wealth or influence. And because books were not widely available in general, not many people could read. But once he made his printing press, he really did achieve his goal of accessibility of books. And in fact, it led to this revolution in mass communication that we're really seeing in Europe for the first time, as well as a boom in literacy. So it's not just that Gutenberg invented the printing press near the beginning of the Renaissance. It's more accurate to say that his printing press is really one of the things that caused the Renaissance period. Suddenly more people had access to written work, which led to making education in general more accessible, and it allowed the spread of news. It led to social revolutions. It allowed for the toppling of certain classist structures in society, because now suddenly every average person can have access to this kind of knowledge. It just completely revolutionized the way that European folks disseminated information. And so in that way, although it's difficult to imagine the impact of being alive at that time and the impact of the printing press, it's kind of similar to the invention of the internet in terms of how quickly and widespread it changed the way that we communicate information and have access to knowledge. Then following the Renaissance, the printing press arrived in colonial America in the mid-18th century. And then together, America and Europe, the Western powers, went through what we call the Industrial Revolution. And during the Industrial Revolution, we saw the printing press really change form drastically. There was a transition to these like man-operated, sort of hand-powered printing presses towards these giant steam-powered rotary presses. And we start to see things like newspapers, and greater materials being printed. Very, things being printed every single day, different things being printed every single day, and just print becoming very, very commonplace in society. But it should be noted that even though the form of the printing press was changing during this time, the basic principles of the press remained the same, founded in Gutenberg's sort of layout for the printing press, specifically in the way the types were casted and in the way the ink was made and the way the ink was applied. So Gutenberg's influence very much is still lasting. And the only time we see a really, really stark contrast away from his original mechanical printing idea is towards the late 80s, when we start to have digital print. And that is the type of print really that we mainly use today. Mechanical presses do still exist around the world, and especially for newspapers. For example, the New York Times has this really big mechanical printing plant that's really amazing. But otherwise, on a day-to-day basis, we use digital printers, and it's kind of amazing to consider how far printing has come, especially because now we can have a printer in our house, and especially since digital printers are so reliable and easy to use, and they always work, and they never break down on you, and you never have to worry about any. No, I'm joking. But seriously, Gutenberg's impact was profound, and there's no question that his press truly did change the world. So it's totally understandable why his press is appearing in all of these top 10 lists of cool inventions attached to his name. However, the Gutenberg's printing press is only a piece of the history of movable type print. Many of the original Gutenberg Bibles remain preserved to this day, but the oldest document printed on a movable type printing press that we have preserved today is not one of those Bibles. It wasn't printed on a Gutenberg press, and in fact, it wasn't even printed in Europe.
China.
It was printed on the other side of the world in Korea.
Korea.
A Buddhist text called Jikji, and it was printed in Cheongju in 1377, which is nearly 80 years before Gutenberg first printed his Bible. And in fact, that 80-year gap for the printing of the Jikji is just the tip of the iceberg when it comes to these East Asian printing methods. There's actually a rich history of East Asian printing. And when I say East Asian, I'm specifically in China and Korea, were hubs of printing. And there's their history of printing stretches back hundreds of years before even the timeline that I've shown on the screen here. Early East Asian printing utilized woodblock printing, where you have a giant piece of wood the size of your page and you carve your entire page into it and then use that to mass produce documents. Many of these woodblock printed texts were Buddhist texts. So it's very interesting that in both East Asia and in Europe, this drive to print was a religious one. Although Gutenberg's drive to make the Bible was so that most people could have a Bible in their home, whereas the Buddhist woodblock print tradition in Korea was much more of an elite thing, and it was something done by Buddhist monks in monasteries, and very beautiful tradition and practice. But there were other types of prints aside from Buddhist document woodblock prints. For example, there were some woodblock prints that were just used for general history keeping. And it's in one of these woodblock prints that was reprinted in the last 100 years or so that we actually see record in 1234 of a Korean movable type printing press. There was recorded record of describing the creation of this press. And that's 1234, which is over 200 years before Gutenberg's press. So the oldest document we have today is from 1377, but we know that at least 200 years before Gutenberg's press, the Koreans had a movable type printing press. If you didn't know about this Korean printing history, you're not alone. Not many people outside East Asia have any knowledge that the printing presses existed before Gutenberg, which points to a stark difference between the two realms of printing. Gutenberg's press spread immediately, while the Korean press did not. And there are many possible reasons for this. One is a matter of, like I mentioned before, who is actually using these printed documents. Gutenberg's Bibles were meant to make reading more accessible, while often the printed Buddhist texts were reserved for more elite members of Korean society. And another really, really big important factor here is the difference in language. Gutenberg was using the 26-character Roman alphabet, but the Korean presses during this time, they were using a version of the Chinese script, which contains tens of thousands of characters. So that, combined with the fact that during this early period in Korea, during the Goryeo dynasty, there were many wars for which they used metal weapons. It wasn't really always realistic to take up a lot of metal to make all of the casts you need for the characters that you'd have to print with. So it's another reason why printing with metal types in Korea was not something that spread much. It was something relatively difficult to do, especially compared to woodblock printing, and it was something that was reserved for a small portion of the population. And then on top of that, Korea's sort of cultural and linguistic history is way too complex to show on this timeline, but very roughly, the transition to the much simpler Hangul alphabet, which uses 24 characters and is a phonetic alphabet, that took about half a millennium, I guess. It took about 500 years to make that happen. And so all of this sort of contributes to why, even though the Koreans had a printing press before Gutenberg, it was not widely adopted outside of very specific circumstances.
So did Gutenberg know about it?
Now, recall that the Jikji is the oldest printed document that we have on record. And it wasn't until the 19th century, when a French diplomat acquired it and brought it to Paris, that the Western world at large was actually made aware of East Asian printing. And the Jikji has sat in the BNF, the Bibliothèque Nationale de France, ever since then, and it's actually there right now as we speak. And in about 20 years ago, in 2001, it was declared a UNESCO Memory of the World. So just taking a large look at this timeline, even if you don't read it, just sort of blur your eyes and look at the red versus the blue, two big facts emerge that can summarize this whole history. One, Gutenberg's press had a much larger impact on the world than the Korean press did. And two, the Korean printing press was undeniably before Gutenberg's printing press. Now, what interests scholars is this initial period right here. So when I asked the question of tracing the origins of printing, what I'm really asking is, was there any connection between the Eastern and Western printing worlds that inspired Gutenberg's printing press? Was he aware of these pre-existing printing presses when he made his? Did he take any influence? It's a very, very contentious question, obviously, and one for which there really isn't any strong evidence either way. There's nothing to really, really, really suggest that Gutenberg was influenced, but there's also nothing to really, really suggest that he wasn't. Scholars from around the globe have studied this topic extensively, trying to figure out if Gutenberg made his press in isolation 80 years, or I guess a little over 200 years after the Koreans, or if there was a connection similar to the Silk Road that we might call the Type Road.
Well, I would ask about.
And now, or like I mentioned kind of at the beginning of the talk, scholars have kind of hit that wall of the limit to how much that they can uncover just by studying the history and by studying certain written accounts. And so this is where X-ray physicists step in.
Okay, this is
so we're turning towards X-ray spectroscopy to try to shed new light on this whole research subject and learn more about early print. We're essentially just scanning some of these preserved documents, looking for clues to try to answer this question about whether or not we can trace the origins of printing. And it should be noted that my work is part of a much larger UNESCO-funded collaboration called From Jikji to Gutenberg, sort of symbolically hinting at, if anything interesting happened between the printing of the Jikji and Gutenberg's creation of his printing press. This collaboration brings together print scholars from across Europe, and then specifically Korea, and then America. So on the team are paper experts, ink experts, type experts, conservationists, librarians, private collectors, and of course, 2 physicists, being my PI and myself. And I've got the link to the collaboration on the slide here, if you're curious to check out sort of more detail on all of the many, many, many people that are involved in this. So through this collaboration, we gained access to these beautifully preserved early printed documents. So in particular, we had about 20 Western leaves that were lent to us from the Stanford libraries. They're very individual pieces of paper from early print, closely following the invention of the Gutenberg printing press. And actually, this Western leaf that's on the screen right now is from a printing of the Canterbury Tales, specifically the Knight's Tale from around 1470. And then we also had 40 Korean leaves that were brought over by our Korean collaborators, which were printed between the 14th and 18th centuries, so pre-Gutenberg to a couple of centuries after Gutenberg. Specifically, our collaborator, Angelica No, who works for the International Documentary Cultural Heritage branch of UNESCO in Korea, she brought over these 40 leaves in a trapper keeper in her carry-on bag. So that was the difference between conservationists culturally was very interesting to watch. Of course, they were preserved beautifully, and we were able to mount those. And then finally, and most notably, from a mysterious private collector from somewhere in Virginia, we actually were lent several leaves of an original Gutenberg Bible. So that is a page of one of them. And you can see the printed words. And in addition, there were these beautiful rubricing, this painting embellishments that were done afterwards to beautify the document. And then from the same collector, we had a full bound Confucius text. And this is believed to be printed just a couple years before the Gutenberg Bible. So these were kind of our 2 big pieces to offer us the most direct comparison about that really early Gutenberg period. We studied these documents using X-rays. So now that we kind of have a solid foundation in the history of print and the setup of our whole experiment, it's time to dive into the science. So we used X-rays to study these documents, and specifically a technique called X-ray fluorescence. But before I explain what that means, I need to explain what X-rays mean. So X-rays are a type of electromagnetic wave which fall on something called the electromagnetic spectrum. So this image here is something you may have seen in a previous science class before, but basically different electromagnetic waves are differentiated by how energetic they are. And the energy of a wave is inversely related to its wavelength. So wavelength is literally the physical distance in space that this wave takes up as it travels. So down here at the long wavelength end of the spectrum, we have the lowest energy waves, which would be radio waves, which have wavelengths on this order of miles. And that's why a radio station can send out these very long waves and they will reach you wherever you are. It's also why if a radio wave hits you, nothing's going to happen to you because it's so low energy. And then moving up in energy, we have microwaves, which are used in microwaves, just energetic enough to excite the electrons in your food and heat them up, but not energetic enough to do any sort of damage to you. And then moving to the middle of the spectrum, we have sort of the colored light range. So right in the middle is the visible light spectrum. So that's all the light that we literally see with our eyes. When you're out in the world and you see different colored things, that is light being reflected off of an object at a certain wavelength, and then your eye perceives that. It's also the reason why if it's completely dark in a room, you won't see anything. There could be light waves that you were being exposed to, but if they're not in the visible light range, you won't see anything. So the lowest energy, longest wavelength, visible light is red. And just below the visible red is the infrared. And that's usually light that's given off by heat and radiation due to heat. And actually, it's actually possible to see the infrared by wearing specific goggles that kind of shift the wavelength up and pull infrared light up into the visible light. So those are kind of infrared goggles, or maybe the cooler name would be like heat signature goggles that you see a lot in spy movies and things like that. That's actually real. And then the highest energy visible light is ultraviolet. It's violet. And so just like infrared is below red, above violet is ultraviolet. And now ultraviolet is sort of the range where you start to enter, where the light starts to get a little bit dangerous. By that, I mean the light can actually harm organic matter or very fragile matter. Obviously, the ultraviolet is not that strong. The only danger to ultraviolet is like prolonged exposure to it with no protection. So ultraviolet light is most commonly given off by the sun, which is why you're encouraged to wear sunscreen and sunglasses when you spend a long time in the sun. And then towards the very end of the ultraviolet spectrum, you enter extreme ultraviolet and then X-rays. So this is our target range here, where the energy level in X-ray towards the lower end of the spectrum can be safe to use on human bodies, and we actually do that all the time at doctors' offices. But towards the higher end of the spectrum, you start to hit hard X-rays, which can be a little more dangerous. So when you go to the doctor's office, they expose you to X-rays on the target part of your body for just a very, very brief amount of time. And those X-rays are usually strong enough to penetrate through your flesh and your blood, but not harder things like your bones. Or for example, metal, if you've got metal body parts, or if you swallowed a coin or something, those would all show up in an X-ray. So when we want to study our cultural heritage objects, we don't use the level of X-ray that you'd have at a doctor's office. Instead, we use much higher level X-rays, higher energy X-rays. And the key here, again, similar to a doctor's office, is to only expose the sample to X-ray for a very short period of time on the scale of milliseconds. So even though these X-rays are very high energy, they won't actually damage the document. It's only when you go beyond X-rays into the gamma ray territory that you really risk damaging the documents a lot, but we do not deal in gamma rays. So now specifically the technique we use with these super high energy X-rays is called X-ray fluorescence. And to explain that, here I have this sort of rudimentary model of an atom where the red center in the middle is the nucleus of the atom, and all the little shells around it are electron shells, and all the dots are electrons. So the first step of X-ray fluorescence is to hit your sample, to hit an atom with an X-ray. And this X-ray is high enough energy that it will knock an inner core electron out of its shell. So the nucleus of an atom is positively charged, if you remember from chemistry class, positively charged because it has protons in it, whereas electrons are negatively charged. And positive and negative charged things have an attractive force on them. So the inner core shell electrons are very, very, very tightly bound to that nucleus. So in order to rip them off the atom, you need something that is as high energy as an X-ray, especially as you go to heavier and heavier elements, because the nucleus will get more and more positive. So you choose an X-ray of the right energy range that it can knock out an electron of your
Then do X-ray fluorescence with microscope.
And then that core electron just sort of gets ejected and it leaves behind this hole. And due to the way electrons arrange themselves around atoms, you're not allowed to have that hole. It has to be filled by another electron. So a nearby electron from a nearby energy shell will drop down to fill that hole. Now, depending on how many energy shells are on this atom, the hole that was left by that backfilling electron will also have to be replaced, and so on and so on. But it's this inner shell transition that is the most important, because it will have the most significant energy difference between the shell that it dropped out of and the hole that it's filling. And that is relevant because when the electron drops down to fill the hole, it's got to get rid of that energy difference. And it does that by emitting what we call an XRF, X-ray fluorescence photon. So that is just a little packet of energy, which you can also think of as a light wave. And in this packet of energy will also be in the X-ray range. So it's a very high energy photon that comes out of the atom because you knocked one of the inner shell electrons out.
If he did, I wouldn't have understood.
Why this matters at all is because that photon that it releases, if we can measure that, so we hit our sample with X-rays and measure the stuff that comes off of it, we can actually trace the photons that we measure back to exactly which type of atom was sitting in the sample, meaning that the energy of these photons that fluoresce off of the sample have element-specific energy. So the reason that is kind of relating back to what I mentioned before. If we take a look at the periodic table, the one thing that differentiates every element from every other element on the periodic table is the number of protons in the nucleus. So the amount of positive charge in the nucleus. Starting with hydrogen, you only have one proton. And as you move along, you add more and more and more protons. But those energy shells around the nucleus, or those electrons and the number of electrons in each shell, those don't change between elements. You do add more electrons, but you'll still have 2 in that original shell, and then so on and so forth. So what that means is, as you go to a heavier and heavier atom, you have a stronger and stronger pull on those inner core electrons, which means every time you rip an electron out of the inner shell, it's going to be a different energy that gets released for every single atom, because there's a different pull on the electrons in every single atom. So the idea with X-ray fluorescence is if you can hit any type of sample with these X-rays and measure the fluorescence that comes off of it, we can have an exact sort of measurement of what the atoms sitting at that sample were. And what you generate from this type of experiment is something called an XRF spectrum. So this is what that looks like. And on the x-axis, we have the energy of that photon. On the y-axis, we have the intensity. So a stronger peak means that you got a lot more of those types of photons, which indicates there's a lot more of that type of element. And every single value on the x-axis, we can kind of trace back to a certain type of element. So for example, this big, whatever sample this came from, this big peak here is coming from a copper signal, which means that this sample contained a lot of copper. And similarly, it contained a lot of iron and calcium and so on. Here, when you see the Ks and the alphas and the betas and whatnot, that's referring to a specific type of transition. Those change depending on where the original hole was left and which type of electron went to fill the hole. But in general, the alphas are the strongest signal, followed by the betas and so forth. So this technique is really, really useful for elemental mapping. What that means is, imagine this sample right here is generated by hitting a sample at one spot with an X-ray. But if you rastered your X-ray across your whole sample, you could effectively get one of these spectrum for every single pixel of your sample. And then you could filter all of your pixels by, say, copper, and then you would see an image of your sample and it would light up everywhere there's copper. So this is a very, very useful way to sort of visually analyze what's going on in the sample. So now that we know the technique, we move into the actual experiment. So in order to generate these very high-powered X-rays, we have to go to a particle accelerator. And the specific type of particle accelerator is called a synchrotron, which is a very cool word. And it's very hard to say. And specifically, we went to the Stanford Synchrotron Radiation Light Source, or SSRL. And here's the logo of SSRL, which I think is actually very useful to describe how it works. So this facility is made up of 2 small synchrotrons, each one being one of these rings. And the way a synchrotron works is you pull electrons off of some substance, like you pull electrons off of a metal, and you shoot them through this ring. And depending on how you modulate the electric field in the ring, these electrons will get faster and faster and faster and faster. So this smaller ring makes them go very, very fast, close to the speed of light. And then as soon as they're going fast enough, they get injected into this bigger ring. And the thing about electrons is that when you make them turn, when you make them change direction, they have to give off energy. They can't turn in one direction without giving off energy in the opposite direction. And so because they're moving so fast, the energy that it gives off is actually really high energy. It's actually in the X-ray range. And so what this storage ring does is, in addition to the electric field, there's also a modulated magnetic field, which keeps the electrons going at the same speed. So effectively what they're doing is they're just spinning around in circles endlessly at the same speed, constantly shooting off X-rays. And those X-rays are funneled into little beamline stations where experiments occur. And those are all sort of where these arrows are, kind of tangentially from this circle. You can run a little experiment at the end of every single one of these arrows. So at the actual facility, here's a literal picture of it from the sky. You can see here's the booster ring and here's the storage ring. And our experiment took place here at this facility. It was a week long, the last week of July of this year. And here's what the actual beamline station looked like. So it's kind of this big metal box. This no through traffic is a joke. Everything is very funny at the beamline. There's lots of dinosaur toys and cars and things like that. Everybody likes to have fun there. But this inside this box, X-rays are being shot out. So it's a very, very protected box. You cannot go inside if X-rays are being shot out because there's, a very small chance of danger. And these walls are lead walls, and the glass is also lead doped glass. So X-rays cannot emerge from the chamber. And if we go inside, this is what the beam line looks like. We have our sample mounted in this frame. Right now, there's, I believe, the Canterbury Tales document sitting in there. And then X-rays get shot at it and the fluorescence gets measured. And this everybody else sort of stands outside here watching and analyzing the data as it comes through.
Everybody else.
So just some little notes about the setup to this experiment. There was a lot of work put into mounting these samples. These documents are several hundred years old. And so we had the head of conservation and a separate conservationist from the Stanford libraries come and help us mount them very carefully inside these mats. And then when it came to the actual bound books, like the Gutenberg Bible and the Confucius text, we had to get a little bit creative with how we mounted those. So this is Uva and I at around midnight, the night before we were going to scan that document, trying to figure out the best way to mount it, which we did figure out. And there it is mounted actually in the beamline. So there's a recreation of the beamline upstairs in a lab, which we then transferred to the beamline. And there's the head conservationist, Kristen, checking that we are doing everything correctly. A very rigorous process involving many different types of people. So here's an actual document mounted. This is actually the Confucius text mounted. We kind of had to mount it vertically. And what's going on is the X-rays come out of this tube here that ends in this big pizza slice thing. They hit the document and the fluorescence comes off, a lot of the fluorescence comes off at a 90-degree angle and it goes into this detector here. And so the X-ray and the detector, those don't ever move. And instead it's this metal frame in the background that scans. And we end up getting this whole rastered image of whatever our scan area is. And we can come up with an elemental map. So for example, here is an elemental map of this document. Right now, we're just filtering to show one element out of the many elements. Remember, at every single pixel in this image, there's an entire XRF spectra. So just picture this, you're sitting in the beamline as this document is scanning and it's slowly filling up on the computer screen. And I'm watching it come through and I'm seeing exactly the type of page that I saw, that I was holding with my own two hands. And I was watching this come on the screen and I was like, oh, this is so cool. Like, look at it come up. And I turn around and I look at all the beamline technicians and my PI and the conservators and everybody else who's in there who has done this a lot more than me. And they are all just standing there with their jaws dropped. They could not believe that we got this kind of signal. Specifically, what I'm referring to is the spatial correlation of this signal. So what's going on here is everywhere that you see red, there's a very strong signal of this element versus everywhere that you see blue, there's a very weak signal. So what we're seeing here is we've clearly picked up an element that is only in the ink printed portions of this document. And the reason that was so shocking is because we were told by scholars that these inks are largely carbon-based. And if you know, carbon is a very, very light element, which doesn't actually show up in these scans because it's too light. And we weren't actually expecting to pick up any heavier elements like metals. And instead, that's exactly what we saw here. In fact, this instrument is so precise that you'll notice in the bottom left-hand corner of this image, there's this big smudge here. And that smudge is actually exactly where you put your hand to turn the page. So the smudge appeared in several channels, as particularly chlorine and calcium from all the sweat that has come off of hands turning the page. So the instrument is that precise that it can pick up things like sweat or even a fingerprint or something like that. So we ended up generating this wealth of scans and information. And from there, the big task is to analyze this data.
Still didn't say what it was.
So jumping into the data, this is sort of the analysis of the data is what I've been kind of doing for the past 3 months. And here's the repeat of that scan that I just showed you. It's from the Confucius text. And actually, this is a copper map.
Right.
So it's not just that we see this amazing signal, spatial signal coming from just the ink, but it's a metal, which is not something that we were expecting to see. So this raises the question of where did this metal come from? One option is it could be from the ink, meaning that when the ink was mixed, metal was an ingredient in the ink. Now, this is something that we've had to discuss a lot with scholars. There are certain ink experts who believe that there should not be any metal. Metal was not an ingredient in these Korean inks at all. Whereas there are some conservators who say that metal is often added to preserve the ink, particularly in Korean inks, which use animal glue to bind them to pages. So it's this whole game of taking this literal data that we get and matching it to the accounts of historians to try to figure out what's going on. Another hypothesis is that the ink, metal was not an ingredient in the ink, but the ink was mixed in a metal bowl. So some of the Korean scholars said that ink was often mixed in a copper bowl. And because the ink itself is kind of a chemical, it's possible that it has interacted with the metal and pulled some of the metal out of the bowl into the ink, and that's the signal we're seeing. But of course, if that's possible to pull metal from the bowl, it must also be possible to pull metal from the types. And this is sort of the million-dollar question of, are we seeing the trace of the actual printing press itself in these images? If that is true, then there's a huge amount of knowledge about these presses and how they were made that we can pull from these pictures like they are time capsules of the presses themselves.
Oh, maybe.
So just to show you some more data, here is the XRF spectrum of that page that I just showed you. And it's a little different from the previous one I showed you, where in the red, we see all of the elements that appear in the ink. And in the blue, we see all of the elements that appear in the paper. So every time you scan the ink segments, you're also scanning the paper segments. So the way to derive any meaning from this is to check which elements are in the ink, but not in the paper. And those are really the elements that make up the composition of the ink. So in particular, we see a high copper signal. And that's, again, that map that I just showed you. Copper is a huge element of only really the ink and not the paper. We see kind of a higher element of phosphorus, iron, and lead, but it's not nearly as striking of a difference as it is with copper. Whereas when we look at a similar scan for the Gutenberg leaf, we see, in addition to copper being heavily present in the ink, we see lead as well. So this was another thing that we spent hours and hours discussing with the European print scholars, as they believe there's no reason that lead should appear in the print, but they know that the types were made of lead. So we have a lot of different clues pointing us in different directions. And right now, we really have to be extremely careful making any sort of claims. I hesitate to make any claims to you all, and I also am restricted in what kind of images I can show you based on what is going to be published and what is not going to be published. But suffice it to say, we have so much more information than we were expecting to get from these pages, and the information is very, very, very promising to reveal more about these documents. Another interesting aspect to our scans is just in the way that these metal signatures appear. So these are both copper maps from the Confucius text and the Gutenberg Bible. And remember, red is a strong signal, blue, green is a lower as a less strong signal. And you'll notice a huge difference between the Confucius text and the Gutenberg text are that the Confucius text seems to have this little halo around the characters, where the characters are appearing in red and then they have this light green halo. And that halo is not visible to the eye, but it is something that is chemically picked up by the XRF, which indicates that these metals are bleeding a little bit into the paper. So that kind of adds an entire other element to this process and is another kind of clue in our toolbox of whether or not where this ink came from. Versus in the Gutenberg Bible, we don't really see that halo effect at all. So again, there are multiple reasons for this. It could be from differences in where the copper came from, and it could also be differences in how the documents were preserved.
And that's what's probably happening there.
The Gutenberg Bibles were under conservatorship for hundreds of years, a very, very long time, very like meticulously cared for. Although actually the Gutenberg Bible leaves that we did have were part of a Bible that was in a fire, and only a few leaves survived, and we got those leaves. So there are many, many questions. And it's very interesting that we have the hard evidence from the XRF, but we have to go back to more subjective pieces of information about these experiments to understand why we see those in the first place. Here is another example of, I always like to show this type of image to show the sensitivity of our scan. So this is a scan of a Korean 18th century document, kind of a later one. And what you'll notice is that our element-specific filtering can actually filter out different parts of the page. So what we see in copper, those are all printed, versus what only is showing up in the mercury channel. Those are actually red circles. Those are red ink that were drawn on after the fact. And so that red ink is known to contain a lot of different metals, including mercury and nickel and copper. So it appears in the copper channel, but in the mercury channel, it's the only thing that appears because it's the only place you see mercury. And similarly, in the calcium channel, we see this little smudge of something that was on there, which is very funny, kind of flicking through the channels on our software. Sometimes things pop out at you that you absolutely did not see with your eyes, especially on a lot of these Korean documents. Some of them have liquids that were spilled on them. Some of them have pieces that were removed and taped back in. And not a lot of these elements you can actually notice until you look at the XRF spectrum. So right now, we're still in the process of analyzing all that data and sort of making sure we know what it means before we say anything to anybody. But we do have plans in the works. Our next experiment is actually in a couple weeks. It's the first week of December. I will be going back to Stanford to run the next round of experiments. And the really fun thing about this whole project in general is that we are building our next experiments based on the results of the previous experiments. So because we got so much useful information from this past experiment, in this next experiment, we are going to try to answer some of the questions that came up in this experiment. So one of our big new elements to this upcoming experiment is that one of our collaborators from the Netherlands, who is an ink and print expert, he actually handmade ink and acquired some types from which he knows the exact composition, and he has created his own hand prints. So essentially, we know exactly what's in the ink, we know exactly how the ink was made, we know exactly what type of bowl it was mixed in, and we know exactly what the type is made out of. And we have these new prints, and we're going to scan those in the XRF. And if we see the same type of signatures, if we see the metal appear, for example, and we know that the metal was only in the type and not in the ink, then that is a basis to compare with our past data to try to track down where the metal came from. Similarly, if we see that sort of halo effect, then we can compare it to his actual printing methods to figure out where that came from. So we're in this kind of stage where we're trying to recreate the printing conditions so that we can actually trace where some of these effects that we see are coming from. The other element to this experiment is we're going to try a couple other, or mainly one other X-ray spectroscopy method. So XRF allows you to see exactly which element on the periodic table is sitting in your sample, but there are some different electronic X-ray spectroscopy methods that allow you to tell the chemical state of an element. So we know this is copper here, but is it copper 2+, which is missing 2 electrons, because that might indicate it's bound in a certain way. Or is it just regular copper? That will indicate that it's a pure metal. All of these things are just trying to get us closer to figuring out why we saw the things we saw, which then will help us trace the origins of printing. Thank you so much. And I just wanted to give a shout out to the fraction of the Jikji to Gutenberg team that was actually on the ground with us in the beamline and made this possible. Thank you for listening to my talk.
Questions? Sure.
Yeah.
Have you done any of the XRF spectroscopy of wood print?
Yes.
And how did that differ?
Yes, we have. Field, which means that we're not detecting any sort of metal from the print. So that was, we believe that to be kind of a smoking gun, that in the metal type prints, if we see metal, it must be coming from the type, but that's not entirely true, confirmed. We are discussing extensively with the Korean scholars, and there is a hypothesis that different inks were made differently depending on if it was wood or metal, because getting the ink to transfer from wood to paper versus metal to paper, you need to make the ink differently. Another thing to note actually is that on this copper scan here, there are these few characters up here where we kind of see a negative image of the character. So here we're seeing the strong copper signal over the characters, meaning they were pressed in from a type. But here we see a strong copper signal around the characters, and that's actually indicative that these little pieces were tiny wood block pieces that were inserted in there. And we still see this strong metal signal on those wood block pieces. So again, kind of contradictory pieces of evidence that we are sorting through right now. But yeah, that's a very good question. We would also love to see European woodblock prints, and we're working on trying to get one of those. Oh.
You mentioned, well, you said that there's going to be carbon, you saw carbon in your spectra. But then when you showed the spectrum, I didn't see carbon on that spectrum right there.
Right. So we expected from the scholars that we would see a lot of carbon. It was kind of like a historical evidence that these were big carbon-based inks with things in it, like, for example, graphite with pencils is a carbon. And the reason we don't see it in the spectrum is because it's too light. So if we look at the periodic table, carbon is up here at 6. And so what that means is that the nucleus does not have a very powerful hold on its electrons. So it doesn't take very much energy at all to knock them off. And so the photon that we get out here, this element-specific energy, very, very small. And it kind of dissipates before it has the chance to reach the detector. So actually the limit on the elements that we can see is kind of around phosphorus. So elements that are below phosphorus on the periodic table, we cannot really see a strong signal for them.
Yeah, I knew right off that tribology would be in this topic. When you're going to do your experiment with the type block on paper that your colleague in the Netherlands is doing, make sure that he understands the effect of pressure.
Right.
Because there is a creep phenomena that takes place whereby the paper will translate while it is being compressed. That gives rise to wear, which can take the metal off the plates.
Right. Yes. And actually, it's very good that you mentioned that. This very specific collaborator actually wrote a paper on that exact effect that you mentioned. So it's something that he was really paying attention to. And I believe the samples he sent us, not only the different inks, but also pressed in different methods that he is very meticulously pointed out to us.
Yeah, with that, have you studied the intaglio process of printing?
No.
Where they
I
make
believe-
use of that effect?
I do not, if I have not, I do not know, recognize the name of it.
Okay, most paper currency is printed that way.
Okay,
Thank you, very interesting.
yeah, thank you.
Mike.
Yeah, I was just curious, does the type of work that you're doing, does it have any forensic applications?
I think yes, definitely yes. So really anything at all can be put in front of the XRF spectrum, as long as the target elements we're looking for are heavier than phosphorus. You can put anything in there. My PI once told me that he actually, to try to test the beamline, there was this frog outside his door that had unfortunately passed away, and he just picked up the frog and mounted it in the beamline and scanned the frog. So there's all sorts of biological samples that do get scanned here. And I think it could definitely have applications in forensics, I think, particularly if you worked really closely with a chemist that can tell you how certain elements are bound. They can tell you if an element is bound organically or bound inorganically, or if something is metallic. They can really give you, paint a picture of what happened to your sample. That's a very interesting question.
Can you go back to the slide with the energy levels of the paper and the ink? Yeah. And I think I'm more the Gutenberg
Right.
leaf. Yeah. No, it's confused. Okay. So, and then also with the Confucius leaf, the correlation between the paper and the ink, the blue and the red lines.
Mhm.
How do I interpret that? They're almost identical, other than, their peaks. How can paper appear to me on this graph be identical signature to the ink? Or how am I looking at this wrong?
Oh, right. So everywhere you see a peak, the element is present, but I think when you have a significant difference in the y-axis on the peak, it indicates that the element is present mainly only in the stronger signal, if that makes sense. So I think if I really blew this graph up a lot so that you can see the kind of the small ridges in it. But for example, if you look at sulfur down here, the blue line is flat, but the red line peaks, which means that sulfur is really only present in the ink. And so similarly here, this blue signal is so low compared to the red signal that we really only we effectively only see copper and lead in the ink. And in fact, this tiny signal of the metal down here may be due to that like very, very minuscule bleeding effect.
Yeah, and if you switch over to Confucius, like the iron is peaking and calcium's peaking.
Right.
Pretty close. But it's just amazing how coincident each peak is paper and ink together. Now I'm kind of wondering if somehow molecularly the ink kind of molecularly fogged itself out onto the paper and it's picking it up on the paper. I don't know, I'm not sure. But and I got another question about the Confucius page and the paper. I guess it's paper, right? It's not like a
Right. It's not.
They're obviously, I would think they're different types of paper made differently, maybe different base materials.
Yes.
So I guess that's all I was wondering about that.
Right. Yes. They are made differently, but I think you will see they are definitely made differently. They feel different. They look different, but they do end up having very similar elements because of just the nature of paper. Some of the big differences we see are, well, I guess it's not super apparent here. I think there's a lot there in some of our other scans of some of the other documents. We see, for example, a huge calcium signal, like way above everything else, which indicates treatment with certain types of water. some of the Korean pages were wet before they were printed on, which could be another reason why you see the metal bleed out. Yeah, so I think just the elemental signature in general of the paper appears very similar, but the way the paper is treated causes things to appear differently, which is another thing we've discussed. We have had to discuss a lot with the scholars. It differs by region and it also differs by time period.
Okay. How difficult is it to get your hands like on these documents? Like, do you anticipate being able to scan a lot more of these, or is it kind of like you have to go based off of what you learned over the summer with those documents?
That's a very good question. So when it comes to all of the Western leaves, if I can swoop back to that image, all of the Western leaves that were lent to us by the Stanford libraries, those are pretty easy to attain. I mean, first of all, we were already on Stanford campus, and also Stanford is very generous with their samples. It also helps that my PI has this really long history of studying these super, super special documents. So there's a lot of trust there. People understand at this point that this X-ray is not going to shoot a hole through the paper, and that these documents will be safe, especially because the Stanford specific conservators were on the experiment with us. So the Western leaves were pretty easy to attain. The Gutenberg Bible and the Confucius texts, those were privately owned. So it's all up to the private owner if we get to access them or not. But it just so happens the same person who owned the Bible and the Confucius text was the person who owned the Archimedes and the Galen palimpsest that we saw at the beginning of the experiment. So this, right. So that person whose identity is anonymous, we literally call him Mr. B for billionaire. He's got a very strong bond with my PI. Nobody else really knows him. And he actually works through a handler whose name is Mike. Mike comes and he's the one who always oversees everything, and he's always there watching it. So again, that just has to do with trust. That private owner has a lot of trust, and as long as Mike is available, we can have these two texts at the experiment. However, the Korean leaves were really the most difficult. And it wasn't because there was distrust to put them in front of an X-ray beam. That was totally fine. It was more that these UNESCO collaborators had to get very, very extensive clearance from the Korean government to remove cultural heritage objects from the country. So that was a very difficult process. And Angelica, the courier, she told me that they actually got in some trouble when they re-entered the country. I'm not sure what kind of trouble. She did say the words, "I thought I was going to jail." So I don't know what that means. The documents are totally fine, but I think they don't really want to go through the hassle of having to do all that to bring them again. So we are just in discussions with the synchrotron that's in Pohang, Korea, and potentially next year going to Pohang to do an experiment just so that they stay in the country, because it would be much easier to scan them. But it is possible that we won't get access to these specific leaves. However, we've worked with a couple other documents that are already in circulation in the libraries in America that contain these different early printed Korean documents. And we actually are getting some of those newer ones to scan during this upcoming November experiment. So in November, we will have the Western and Korean leaves. Mike was not available for this one, but we will also have those newly printed documents, and we'll have different documents that we didn't get to scan before.
So you mentioned that this work was really interdisciplinary. So I was wondering, what was the most interesting part for you to see all these different fields of knowledge come together? Or maybe what was the most surprising part of the process?
That's a good question. I think it's always really, really interesting on one hand when you're around people who are experts in something you have no idea about. So just hearing these scholars talk and present their perspective, it's just, you're kind of in awe of them. But on the other hand, it's also a very interesting experience to be the person who has expertise that nobody else has. So I've gotten a lot of opportunities to explain some really high-level concepts to these workers or to these collaborators. There were also several press interviews surrounding this experiment, and I think learning how to speak to them was really, really exciting. But I think one of the funniest things is the things that the physicists find exciting versus what the scholars find exciting. For example, when we had this image And also when I finally understood the importance of this image, we were preparing this presentation. It was like every night we would have a Zoom call with our collaborators in Korea and give them a little update about what was going on. And I was kind of explaining everything. And of course, there's always a delay because the translators have to talk after every sentence you give. I was really ramping it up. I was like, are you ready for this? You're really not ready for this. And I put it on the screen and I was like, this is the copper signal. And none of them cared at all. And they just stared at it. And then somebody spoke, and the translator, who was very definitely trying to be a little nicer to me than I think what the scientist said that we already knew that the types were made out of copper. And I was like, no, but you don't understand. Like, how could that show up in the scan? That's crazy. And like, I was just trying to explain the concepts enough for us to be excited about the same thing. It was really funny, and it was very fun and interesting. Yeah. Yes. Oh, sorry. I'm sorry.
Hi, you did great, by the way. Wow, I'm like, would there be any value in or anything interesting that you could learn from looking at the same texts again to see how the X-rays affected anything on the leaves at all?
Yes. So, in fact, when I say it's very safe to use X-rays on this document and nothing happens to them, it is true. And visually with the naked eye, like we will never see a difference in these documents after scanning them with an X-ray. But on the molecular level, on the atomic level, there is very, very slight alteration to the document, just, an element here or there that gets burned away. Not anything we would ever notice, but it is definitely of great interest to cultural heritage scholars to keep track of how much radiation these documents get exposed to. And in fact, there is this foundation, I believe, also in the Netherlands, that is trying to create something called the radiation passports for these types of objects, where you just kind of like a passport, you keep a record of every time it's been hit by an X-ray and where, so that far along in the future, if there's any sort of effect, it can be tracked. And over time, we can track the effect on them. But again, it's nothing that would visually alter the document significantly at all.
We have a summer home in Iron County, Wisconsin, and the water is loaded with iron.
Oh yeah.
So could you also take that data? This is my first question. Could you take that data and find out where the ink and the paper were treated?
Yes. In fact, kind of generally, we know that, for example, the water that would have been used in Europe versus the water in Korea is very, very, very different. In Europe, there's a lot of like limestone content in the water, whereas in Korea, it's much different, like fresh water content. So just sort of macroscopically placing these, we can definitely do that. I think on the smaller scale, exactly finding the exact location in their country where they were printed, I have to believe that it's possible, especially if we do the different X-ray techniques that allow you to know the exact chemical state of the elements. I think we can be able to do some sort of geographical tracking like that.
Second question is, what does that say?
That's a great question. And, because it is printed in this very, very old Chinese script, not even the Korean collaborators could read it. So that's another thing we need to work on, is having a Chinese scholar specifically in this type of script on the team, because we're not so far. It has not been an issue, the actual content of the documents, but I'm not sure what it says. It is a Buddhist scripture, though.
On this Confucius text, I noticed beneath the two woodblock printed characters in those circles.
Mm-hmm.
Here, there is no mark in one of the circles. When you see it, not in the copper, but in the visible light spectrum, there is a line in one of those circles.
Yes.
Any idea what that line is actually made of, why it's there different from the rest?
Yes, that's a very good question. And it's actually something that the conservators told us to look out for, because upon just visual examination, talking about this little tiny dash that's in the circle there. It doesn't appear in every circle, but it does appear in some, and it's believed to be sort of like a punctuation mark almost, and is believed to be drawn on after the fact. But we weren't sure until we saw it in the scan. So we definitely know that it was drawn on after the fact because it doesn't appear in any of the scans. It doesn't appear in any of the elements where we see everything else that was printed. So it probably is some sort of carbon-based ink, like graphite type of thing. Yes, which is very super interesting.
So first, if you had a detector sensitive down to carbon, would you be able to tell a carbon-based ink from the paper?
That is a very good question. I think my initial intuition is if not yes, then we would, if we don't see a signal that would be sort of like this, the stark difference between the copper and the ink and the paper here, we would probably see something closer to maybe this calcium, where there's so much calcium in the paper, but there's also probably calcium in the ink. I think we would probably see something similar to that. And if we were able to do the X-ray absorption spectroscopies that tell you the chemical state, then maybe we could differentiate the carbon.
The other question is, I was curious, what kind of physical changes do you get from exposure to X-rays? You talked about tracking that, and
yes, I think it is just essentially like very, very, very like atomic scale degradation. So just atoms being burnt off, or just the bonds of very single. How to describe it without making it sound very dangerous? I think just in atoms on the scale of like numbers of atoms being burnt away from the paper, so no longer being there. I think the actual effect on the chemical state is something I'm not completely sure of, how the chemical state of the atom sitting there might change by being just exposed to X-rays. And yes, I think that's just something that we have to investigate more carefully when we start to.
So you think it'd be a matter of breaking some chemical bonds and not actually changing any atom?
Right. That would be my intuition.
So I was wondering, so if there's a limit to how low the amount, like number of protons in the atom that the scan can detect, is there also a limit to how high the amount of protons in the atoms as well?
That is a super amazing question from my precious little brother. So if we go back to the periodic table, actually, if we go back to this model of the atom, the inner shell there that's in pink, we call that the K shell. And then the next shell is the L shell, then the M shell, then down through the alphabet. It starts at K because the guy who discovered it just assumed that there would be more shells inside that he didn't find. So he decided to pick the letter K so we would have letters to go back to. And then it turned out to be the innermost shell. So now we awkwardly start at K and go through the alphabet. But the K shell transitions are the strongest, and those are the ones that are very specific to the element. But again, when we backfill into the K shell, you leave behind another hole, which then gets filled. And when that hole gets filled, it also releases an XRF photon, but it's a much weaker energy because we're dealing with shells that are further away from the nucleus. So every time you do this inner shell backfilling, there's actually a whole backfilling cascade. And it's really only from these inner K, L, and M shells that we get distinguishable energy levels. And, from an L or an M transition in one atom, we may have an energy level that like very closely aligns with, say, the K shell transition of another atom, but we have ways to distinguish it. The problem is you can only get these element-specific K shell transitions for in a certain energy range. So while the lower end is kind of phosphorus, the upper end of our synchrotron beamline is around selenium and bromine, meaning that like the energy the energy of our X-ray beam is high enough to knock out a core electron of selenium. But, you know, as we go higher, we don't have enough energy to knock out the core electrons of these heavier atoms. But that doesn't mean we don't see their signal. Instead of seeing the K signal, instead we would see the L signal or the M signal, because we wouldn't knock out a K electron, we would knock out an L or an M. So that's why we can see elements that are as heavy as mercury or lead, or even bismuth that are much higher in the periodic table, because we're looking for the lower energy transitions. Yeah, so to answer your question, there isn't really a hard limit on how heavy the element can be. We just have to be a lot more careful analyzing the XRF spectra to make sure that we are seeing the element that we think we're seeing. Yes.
I was just curious. I noticed argon was.
Oh, I'm so sorry. That's my fault.
Very interesting talk, and I'd like to know the results as they unfold. But my question was, what are the potential applications of these experiments that you foresee?
Yeah, I think the applications are just expanding our set of knowledge. In each case of these cultural heritage experiments, it's kind of a historical study. And in terms of applications for future technology, this type of cultural heritage work may not apply, but what it does do is clear up mysteries from the past, things that we just don't have any more information to solve. We can access a whole new set of information using X-rays. So this will clear up things. For example, if it did turn out that Gutenberg was influenced by Korean printing presses, that is a huge piece of history that we completely missed out on for like over half a millennium. So sort of clearing up things and understanding why early humans did what they did and why they made the inventions that they made. I think it is something that can help us better understand our shared cultural history and the way that parts of the world are connected. Especially, I grew up in America. We tend to learn history from a very Western perspective. And sometimes here and there, we learn about things that happen in other parts of the world. But I don't know, personally, sometimes I forget that things happen at the same time. Right? The world was moving forward and advancing all around the world, all at the same time. And so proving a connection like this really brings to the forefront like all the technological advances that were happening in other parts of the world compared to the ones that are very commonly known, like Gutenberg's printing press.
Yeah, thanks. Yeah, I was curious. I noticed in several of the scan charts, there was the presence detected of argon. I was curious, what accounts for that being there?
Right. So argon is a huge element in air. It's a huge element present in air. So typically you will see an argon signal on XRF scans just from the X-ray moving through the air before it hits the sample. And then like fluorescent photons just from X-ray hitting the air will make it into the detector, and then we get an argon signal.
Well, it's actually not that huge. It's about 0.7% in the atmosphere.
Yes, but it is one of the elements that is heavy enough to be detected by XRF. So
it's 8:30. We're half done with the questioning period. It's like a hockey game. I really appreciate you fielding so many questions. I think we ought to give you a break if that's all right. We tend to adjourn to the library if people would like to go over there afterwards. Fascinating talk. Thank you very much.
Thank you.